So the first question is, I want to ask, where does those water or ice come from?
The water that we see in Euclid, or that is deposited on Euclid's mirrors, that mostly is sitting in the multi-layer thermal insulation. That is to enable the satellite or the instruments to maintain a certain temperature. Because on one hand, we have the very hot sun. On the other hand, on the other side of the spacecraft, we have the very cold rest of the universe, and we need stable temperatures. And this multi-layer insulation, that's basically 20 to 40 layers of very thin plastic sheets that are aluminized. They can carry about 1% of their own weight in water, which they absorb on ground in the lab or in the clean rooms. And we have about 10 kilograms of that multi-layer insulation around the instruments and the optics. So there's about 100 grams of water traveling with the instruments and in the vacuum of space that just evaporates over time, over years. And very small amounts are enough to disturb our vision.
Okay. Yes. But before the launch, do we heat up our telescope to remove such kind of water or ice within the multi-layer insulation?
Yes, basically all components. I wouldn't say all components, but all the critical components are baked out on ground to get rid of all kind of chemicals that might evaporate in space. But water is unavoidable because the clean rooms, they need to maintain a relative humidity of about 50% to avoid electrostatic discharge or damages through electrostatic discharging. And even after baking out the multi-layer insulation, the MLI, it reabsorbs about 1% of its own weight within 24 hours. So it's unavoidable. And all satellites basically have this problem. It's nothing unusual for Euclid.
So what you actually did is you measure the flux, coming from some calibration star or calibration galaxy, and to estimate like how much that ice contaminate the mirror, right?
Basically, we have what we measure is we observe the self-calibration field, which is always the same field on the sky, and then we see how the throughput changes. So it's like it's a generic drop. It's probably exponential. And over that, there are some wiggles, which is the interference pattern. So the global loss is from scattering, because you have a rough surface on the mirror. So the scattering increases, and you have some interference effects folded in. We see a very similar curve also by looking at any field on the sky, because we can use Gaia as a reference. So all the fields have been observed with Gaia before, and then we get a very similar curve. So these are the two. It appears that scattering is the dominant effect for flux loss. And we have maybe a fourth of that in amplitude overlaid as interference. So before launch, we did not know how big the scatter loss would be and how big the interference loss would be. And the scatter loss in particular is very, very difficult to model mathematically. And therefore, it's very hard to say how much ice there actually is on the mirror.
Now, how did we do the de-icing?
Yes, yeah. Basically, before launch, we had a generic procedure to heat up or turn on all the heaters in the satellite, and also tilt it a little bit toward the sun to get extra heat into it, because Euclid has limited electric heating power, so to speak, for a full decontamination. So we would need the sun. But then this is a huge thermal disturbance to the satellite, and Euclid needs to be very stable. And if we did that, we would probably lose a large fraction of the calibrations that we took over the last 4 to 5 months. And this is what we wanted to avoid. So we developed a new procedure where we step through each mirror individually and heat it up slightly, not to room temperature, but only from minus 140 degrees to minus 110 degrees. And then a few minutes at that temperature would be enough to evaporate all the ice, and then we can cool down again. So it's minimally invasive decontamination. Well, we have a large number of heaters in the satellite. They were meant for full thermal decontamination, so to bring the entire satellite up to room temperature. That was the original plan before launch. But now we know that we do not want to do that because we would lose a lot of calibration data. And over the last few months, we then developed procedures to, instead of turning on all the heaters simultaneously, we would just select one and turn it on for a few minutes or for an hour to allow the temperature to slowly rise, and then stop and measure whether we restored the original transmission that we wanted.
Okay. So we want not only the heater, but also the sun to heat up the mirrors to do the de-icing.
That would be for a full thermal decontamination of the entire spacecraft. So we want to avoid the sun. We do not want a sun in the telescope because that's a lot of heat. No, it's really just one heating. If I remember correctly, the first mirror we started only has one heating element, and it only heats that single mirror. Then the heat it creeps into the rest of the satellite because it's thermally conductive. And so it's still a thermal disturbance, and we had to wait about 2 days afterwards to reach a thermal equilibrium again. But no sun is involved. It's just that one single heater that we used.
I mean, after the de-icing, and what's the performance of the WIS instrument?
Oh, it's great. We got 15% more light. So this is very nice to have more photons. But the critical thing is that 15% flux loss is a very large correction factor. We would need to correct the data. I mean, we need to reach a relative photometry of better than 1% or about 1%. So correcting for 15% is a very large correction, and it's difficult to do that accurately. So at some point, our corrections are just not reliable anymore, and we need to decontaminate. So we restored the photometric throughput, and I think we also restored the PSF also looks a little better, or hopefully looks a little better, but that is I cannot comment on that yet because the PSF data analysis is much more complicated and takes more time. But in principle, we have a cleaner optical surface, and the PSF should be better.
Yes, of course. Yes. And I mean, in the future, how often do we have to do the de-icing, this procedure?
If the current contamination rate that we observed in the last 6 to 8 months continues, then I think we will need to do it about every 6 months.
Okay.
And it will take probably around 3 to 4 days, let's say.
3 to 4 days.
So it's not an insignificant amount of time, but we can schedule these ahead at a time when Euclid, for example, has already observed a patch of sky, and so it's in a low pressure scheduling period, so to speak. But experiences with other satellites, they show us that the outgassing rate initially after launch is very much higher than later in the mission. So maybe we can get away with once every 12 months, but that's very difficult to forecast. We just need to see how it goes. But now it looks like we have a procedure that works very quick within a few days compared to 4 to 8 weeks for a full thermal decontamination. So it's this is very, very good.
Yes, right. You're right. Okay, my last question. Can you see something about the other satellite, for example, Gaia, Cassini, or Rosetta, about ice contamination, water contamination?
Yeah, Gaia initially experienced very heavy contamination. That is what we wanted to avoid for Euclid, and so the Euclid's design was very much optimized to be a low contamination mission. But we always expected some contamination because we know water is traveling with the satellite into space, and it will come out. We just didn't know how bad it would be and how quickly we would need to decontaminate. So Gaia had that problem. Gaia was decontaminated, I think, 6 times within 2 years until it reached a fairly stable state. And other satellites also experienced contamination. Like you mentioned, Cassini, they decontaminated, I think, 12 times until they flew past Jupiter.
Yeah, right.
It's a very common problem.